The thing that I find really appealing about biomimicry is that it's a transformative approach, and it allows you to go well beyond conventional approaches to sustainability. And I think there are two really big transformations that we need to make. And this connects quite well with some of the stuff that John was talking about. The first of those is shifting from a linear, wasteful, polluting way of using resources to a completely closed loop model. And the second is the difficult and dramatic shift from a carbon economy to a solar economy. And on both of those, I think biomimicry has a hell of a lot of solutions to offer. So just before we start to talk about this, this is a clip, well, it's a slide from Stanley Kubrick's 2001. And it's the moment when the bone has been chucked up in the air, and just before it changes into the spaceship orbiting a distant planet. And I think what we see in those first 20 minutes of 2001 is a whole series of distinctions about the ascent of humans. And I believe that the point that Kubrick was trying to make with this cut from the bone to the spaceship, but arguably the most amazing temporal cut in cinematic history, I think the point he was trying to make is that once humans had discovered fire, how to make tools and weapons and so on, it was really just a matter of time before we dominated our environment and kind of moved beyond the limits of our natural world. And so it's quite easy to think of humans as being sort of omniscient and all-powerful and dominating nature and so on. And certainly a lot of the things that humans have produced, such as modern medicine, the digital revolution, they're absolutely remarkable. But at the same time, there are some things that we've made a hell of a mess of. And I think it is difficult to look at examples in the natural world without feeling a certain sense of humility about humans. So for instance, termites have evolved zero-waste sustainable architecture, solar-powered air conditioning, even sustainable agriculture. And that's something that humans in the 20th century really struggled with. And then another example, this is Aramid Fiber. This demonstrates the difference between the way man makes things and the way that nature does things. This is Aramid Fiber, or Kevlar by another name, the strongest fiber that humans have ever made. And the way that you make that is that you take petroleum, you boil it in sulfuric acid at 750 degrees centigrade, then following the principle that if brute force doesn't work, you clearly haven't used enough, you add extremes of pressure to get the molecules into place. Out of that, you get your fiber, and you get a lot of toxic waste. So extremes of pressure, extremes of temperature, loads of energy, loads of pollution, and all that to do the same as a spider does at room temperature with raw materials of dead flies and water. You know, it does suggest that we've still got quite a bit to learn. And in many ways, that's the sort of background to biomimicry. The fact that there is this amazing storehouse of design ideas, this 3.5 billion year R&D period that we can benefit from. And when I talk about biomimicry, I tend to split it into three different strands. And those are looking at natural forms as a source of inspiration, looking at natural systems, and looking at natural processes. So I'm going to talk about three projects that demonstrate each of those streams of biomimicry. The first one is the Eden project that I was very fortunate to work on for 10 years while at Grimshaw's. And you know, it really was a revelation for us, seeing how many things you can find in nature to help with the design process. And we turn to nature at every stage in the design process, from the very early stage, looking at the way that bubbles intersected, even through to the more detailed stages. We used dragonfly wings to help us resolve some of the steel junctions. And it was quite a tough site. It was a quarry that was still being mined, so we had no way of knowing what the final ground level was going to be. And we had to try and find an architectural idea that could maintain its integrity regardless of what the final ground levels were going to be. So the idea we came up with was to create this string of bubbles, and the diameter of those could be varied to provide the right growing height in the different parts of the building. And then the necklace line that joined those together, that could be varied to suit the topography. We had a rough idea of what the topography was going to end up like, but not much certainty about the final levels. And you can probably just make out there's a line running around that. That was the line formed by the intersection between this bubble model and the 3D terrain model. So if you cut away everything that's below that, that produced the first image that looks something like the finished building. The next challenge was to think about how to structure that. And we knew from a number of natural examples that the most efficient way of creating a spherical surface is by using a geodesic structure, hexagons and pentagons. Then we had to think about how to enclose that. And we needed to find an alternative to glass, because glass is very heavy and quite limited in terms of its unit sizes. So we were familiar with this material, ETFE, which is a high-strength polymer. And the way that you use this is that you put it together in 3 layers, you weld it around the edge, and then you inflate it. And it's that inflation that gives it its rigidity. And the fantastic thing about this material was that you could get it in very large unit sizes. With glass, you're limited to about 10 square meters. Here, the biggest hexagons were about 70 square meters. And it was 1% of the weight of double glazing. So in that respect, it represents a factor 100 saving, achieving the same result, but with 1/100th of the resource input. And we found that we got into a sort of positive cycle in which one breakthrough facilitated another. So with such large units, it meant that we had less steel. With less steel, we were getting more sunlight coming in, which meant that we didn't have to put as much additional energy in winter. With less overall steel weight, it meant that we saved a hell of a lot on the substructure. And at the end of the project, I had very accurate figures for the volume of this building and for the weight of that superstructure. And it turned out that the superstructure was actually lighter than the weight of the air inside the building. And having been through that process, if we had just a slightly bigger budget, slightly better building technology, I'm confident that we could reduce that steel weight by perhaps a factor of another 4. And the way that we could do that is by learning some further tricks from nature. In nature, material is expensive and design is cheap. So what you find is that material is used incredibly sparingly, very efficiently. And in this example of a bone, on the left you can see a diagram of the stresses going through that bone. On the right you can see where the bone concentrates its filaments. And the filaments of bone exactly match the stress diagram. So you have a lot of bone where there's high stresses and no material where there's no stress. And clearly, we can't achieve molecular level manufacturing, which is what nature does. But potentially we can start to approximate it, particularly if rapid prototyping were to shift to rapid manufacturing, because that allows you to turn a computer model directly into a physical model or potentially a building product. So if we could make steel tubes that just had the steel where it needed to be, then they would be bigger in the middle where the bending moments are highest, and they'd be very small at the ends. And I reckon that would allow us to take out a huge amount of further steel weight from that building. So the Eden project is, I think, quite a good example of how you can use natural forms as a source of inspiration to lead on to completely new solutions. And it allowed us to completely reinterpret what was quite an established building type and come up with a scheme that was radically better in terms of the material it was using, in terms of the energy required to run it, and so on.